Stats review part 1. So first we're going to talk about correlation. Now correlation is just a number that lets you know how closely related two quantities are. Now there's different types of correlation. There's a linear correlation like right here. There could be a nonlinear correlation like over here. You have to know what the difference. Then we can talk about the strength of a correlation. Right here we have strong positive. So positive means it's going up, right? So you go from left to right, you're going up, it's positive. So strong positive, you notice all the values are really close to the line. Moderate, you see it's more spread out, and then weak, it's kind of all over the place, but still going up. The same can be said for negative. So if it's going down from left to right, then it's called a negative correlation. And then same ideas, strong, moderate, and weak. We actually have values for these things. So first, the correlation coefficient is R. So R is your correlation coefficient. And we'll talk about how to find this in your calculator in a bit. So that tells you how strong and weak things are. And if R is 1, that we call that perfect correlation. So it's a straight line. So even if it's it has to be a straight line. So even if it's a little bit off, like almost a straight line with the little thing right there, it's not 1. So 1's perfect. And then negative will be perfect negative. Then we have very strong, which is like it's a little bit off like that to be very strong. And then we have strong where it's really close, and then moderate, and then weak, and then no correlation at all. Now they will ask you about this, so you have to understand that perfect has to be perfect. That's what I was saying, it has to be perfect. Very strong is like almost perfect, and then we have strong. So you have to know these. For the most part, you don't have to have them memorized, but have a good idea. I always try to think of 0.95 is very strong, and then below that, 0.87 is strong, and then in the middle is this moderate. It's a big gap here in the moderate. Right, and below 0.5, you can just understand it's weak because it's less than halfway. And then no is like very small. So that's the general idea. Let's do an example with this stuff. So the age and heights of children on the playground are given below. So first one wants to draw a scattered diagram for the data. So I'm going to use this with their calculator. So they could ask you to do this by hand or with the calculator, just drawing a scattered diagram. Either way is fine. I'm going to do the calculator right now. So turn my calculator on. I'm going to go to stat. I'm going to go edit. And I'm going to type all these values in. So I'm going to use L1 for age, for X, and L2 for height. So now I have them all typed in. I've typed in L3 just to show you the way you delete an entry. In case you go too far, you just go to the entry and press delete. If you want to delete the whole column, you want to go there and put clear. Right, very important, you hit clear, not delete, because that will clear it for you. If you hit delete on it, on the L3 part here, it's just in delete L3, and you're like, okay, well, there goes my L3. You can get it back. It's actually super easy to set up editor, but it's still not for the trouble. So there's L1, L2. Now do I want to draw a scatter diagram? So I'm going to go to stat plot. I'm going to turn one of these things on, hit on, and then in this case we want a scatter plot, so that's fine. L1, L2, that's all good. Okay, graph, and I don't see anything. It's because my window's off. Now there's a couple ways you can do it. You can fix your window yourself. Go to window, make your lowest like 0, right? Make your highest, it looks like 15-ish. Change your Y to, I don't know, 0 to 150. Or you could go to zoom, and then toward the bottom there's the zoom stats. There we go, number 9 I should say. And then it'll have like a nice little graph for you. So that's my scattered diagram of the data. Now they want you to use technology to find the least squares regression. Another way to say this is they want you to find the regression equation. So we don't have to worry about the least squares part, just find the regression equation. And a lot of times they're also going to ask you to find the correlation coefficient. So which is R. So it's about how to find R and that at the same time. So first with your calculator, the very first thing we gotta make sure actually is that you have the R like enabled. So if you go to mode, toward the bottom, it says stat diagnostic. This should be on. By default, it's off. I don't know why, it's dumb. But so you want to turn it on. And anytime you reset your calculator, make sure it's on. So go stat, turn it on. That gets you the R. Now if we want to find a correlation coefficient, all we have to do is go to stat, go over to calculate, and there's all these regressions. Now in this case, for IB, we're going to mess with the linear regression. So we're going to go to linear regression. And then it looks like that if you're updated. L1, L2. Frequency list. Now I have to watch out. In this case, we don't have a frequency list. You only put that if actually it says frequency. So we're going to leave it at that. Store request. This means, hey, do you want to put it under, like, you want to graph it under a Y? You could do that if you want. Alpha and type whatever Y you want. Most of the time you can leave it blank. It's not a big deal. And then go to calculate. And this is your least square regression line. So that's the linear regression equation. Here's our R. We're not going to do it with R2 in this class. So R is 0.982. 983, sorry, 3 sig figs. So let me do the R first. 0.983. Right? And this is a very strong positive. right? It's more than 0.95. It's a very strong positive correlation, right? So it's around there, very strong positive. And again, that says the height of people, that children at the playground, their age and their height have a very strong correlation. The older you are, the more likely you're going to be taller than the other kids. In your equation though, right? So my least square regression equation, I'm just going to plug these in 3 sig figs. So it's going to be 0.98x plus 80. So let's go. I should stop saying ooh. So 0.598x plus 80.0. So that's my least square regression line. Keep in mind what each thing is, right? X is years and Y is height. At what age would you expect children to reach the height of 140 centimeters? So in that case, look what they're telling me. I'm looking for age, X, and they give me height, Y. So you're just gonna plug it in. Make this 140 equal to 5.98x plus 80. Let's do some math, subtract that. Subtract 80 from both sides, you get 60 equals 5.98. Divide by 5.98. And you get about 10 years old. So around 10 years old, you expect expect children to reach a height of 140 centimeters. D, interpret the gradient of the least square regression line. So they want to interpret the slope. Remember, gradient means slope. That's IB for slope of the least square regression line. So a couple things to keep in mind here, guys. Slope, it's like you always know it, right? It's change of y over change of x. Y over x is what I care about. So our units for slope is y, which is height, over age. And our slope is 5.98, so 5.98 over 1. So what does that mean? When it's positive, it means you're rising 5.98 centimeters for every 1 year. Age is a year. So that's what it means. You grow, on average, 5.98 centimeters per year. That's how you always want to read slope, right? The line is per. So 5.98 centimeters per 1 year. So that's how you interpret the gradient of the least square regression line. By the way, if they ask you to interpret the y-intercept, which I don't have here, actually I have right here 80. That says that's where you start. So at 0, you're 80 centimeters. That's what it's saying, right? Because the y-intercept is 0 and 80. So it's saying at 0 years old, you're 80 centimeters tall. Use a line to predict the height of a 20-year-old. Do you think this prediction is reliable? Right, so if you want to predict the height of a 20, you just plug it in. So it's going to be y equals 5.98 times 20 plus 80. So if I do that on my calculator, times 20 plus 80. There you go. And I get 199.6 centimeters. I have no idea what that is in inches because I'm American. I believe it's actually 2.54. So let's divide that by 2.54. So about 78 inches, which, again, I got to flip that over, divide by 12. About 6.5 feet. Now, do you think this prediction is reliable? I'm actually saying no. 6.5 feet's not crazy tall. Well, I should put the regular, whatever 200 centimeters it was, right? 6.5 feet's not crazy tall, but if you notice, what happens if I ask how tall is a 30-year-old? I'm just gonna plug in 30. This is a linear regression. It says, hey, our height's gonna never stop growing, so that's not gonna work well. So, do I think the prediction is reliable? No, it's not, right? Because it's a linear. It's a linear. It's never gonna stop growing, and people stop growing at a certain height, so it's not reliable. But that's how you do regression lines. Next, let's talk about box and whisker plots. So the general box and whisker plot right here, guys, it's about the 5-number summary, which is our key 5 numbers are our min, our median, our max, right? Median is the middle number. Now, in between the min and the median, we have the lower quartile, Q1, and that's about 25% of your data. That's the median of the bottom half. And then in the median, now the same thing with the top half here. Halfway between the top half, the median of the top half, is Q3. Q2 is the median. That's about 75% of your data. Right, so that's our key numbers. So right here, when I see the 13, I know that's my min. when I see this line, that's my Q1. So that's where 25% of your data is. This line right here is the median. This line right here is Q3. And that line's my max. And that's how you do a Box Whisper plot. You find the min that goes on the very end. You find the max that goes right there. And this middle box here, which has the Q1, the Q3, and the median, that's 50% of your data. That's what we call the middle 50. Which makes sense, right? Because it's 75% and 25%, 50% of your data. So that's how you look. So that's how you look at a Box Whisper plot. What does it tell us? It tells us the min, tells us the max, tells us the median, tells us the median of the bottom half, median of the top half, and it tells us where 50% of our data falls in. So 50% of our data falls between 25 and 47. Some other key things we can learn from this. I completely almost forgot. Interquartile range, right? Interquartile range is the middle 50% of data. It's Q3 minus Q1. And all you do here is go, okay, Q3 is 47, Q1 is 25, and I'm going to get 22. So that's my interquartile range, right? That's how much value is in between the middle 50% of your data. It's a very important concept there. They ask that a lot. So IQR, you have to know it's Q3 minus Q1. Most of the time, you just get a point for writing that down. Also, the range. You almost forgot about the range, right? So the range of data. That's just the max minus the min. So in this problem, our max is 59, and our min is 13. So you get a range of 46. Right? And I think that's pretty much it for Box Whisper plots. Next, let's talk about cumulative frequency tables. Another IB favorite. So in this one, the lifespans of 20 pet goldfish are represented in the frequency table below. So, right, 40 fish live between 0 and 1 years, 72 between 1 and 2 years, and blah, 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 blah. Complete the following cumulative frequency table and draw a computed frequency curve. So in this case, less than 1 year is 40. Right now, remember, cumulative frequency means it's like, what's the running total? So less than 2 years, you're going to add up these two scores here. So it's 40 plus 77, which is 117. Right, so that's adding these two up, because cumulative frequency, right? What's the running total? Between 2 and 3 years, so less than 3 is going to be that, plus another 32. So that's going to be 149. And then less than 4 years, so we're going to add up all these, right? Just add 28 to our 149. And that's about, let's see, 179, 177. And then finally here, we're going to add 23 to that to get less than 5. That's to be 200. Right, and that's how you do a cumulative frequency, right? It's all about finding, okay, have the running total here. So I have 40. I'm going to add the 77 to get 117. I want to get this value here. Well, I'm going to add the 32 to get that, and so on, right? It's a running total. So you're just going to keep on adding this plus this term, and that plus that term, right? Just keep adding it up. Now they want me to draw it. So my value here wants to be 40. So at 1 year, I have 40. Now, 2 years is 117. So at 2 years, I'm about 117. So around there's an estimate. 3 years, I'm at 149. So 3 years, 149. Oof, that's a hard estimate. 4 years is 177. 4 years, 177. And then 5 years was 200. And we always start at 0, and we always end at the max. And I get something to this effect. Something to that effect. Tried my best. Okay, next, calculate the expected lifespan of a goldfish. Now, here's the thing. People always freak out with the expected lifespan, or I should say this expected value. Now, right, if you look at your formula sheet here, everybody goes, okay, expected value is this. You gotta understand, expected value also just means mean. It means average. So it could be this. You could use this. Notice it has the either or two. It could even be this. Expected value is just the mean. So if they say expect, that's just the mean. So how are we going to find the mean of this? Well, the way you find a mean of community frequency is you don't. You use a table right here. And we use our calculator. And actually, we use this table right here, actually, the normal one. L1, L, and for L1 here, now notice that there's like a span of numbers, right? It's a range. Now the way we do it in our calculator is you put the midway point. So 0.5, 1.5, 2.5, 3.5, and 4.5. And we just add up and divide by 2. So I'm going to put this in our calculator. I'm going to go back to stat. I gotta turn it on. Stat, edit. Now I gotta clear all this data, so I'm just going to go here and put clear. And so type them all in. And voila, it looks something like that. Now, how do we actually get the values of our expected value or mean, right? By the way, expected value means mean because expected is like, what do you expect to happen? That's what the mean is. It means the average. What do you expect to happen? So we're going to get out of this. And we're going to go to stats, calculator, and we're going to go to one variable stats. Now remember, in this class, we never use two variable stats. In this page here, in IB, all we ever use is one variable stats and linear regression. That's it. So we're going to use one variable stats. My L1 is my list one. Now keep in mind here, I actually have a frequency list, right? Very important. If it actually says frequency, use the frequency list. So I'll make that L2. So second L2, hit calculate. And my expected value is just the mean, which is this symbol right there. So 2.0936. By the way, let's go over some of this other stuff, right? That's expected value mean. These are both standard deviation. This is the one we use in this class. And this is the total number of things you had. If you scroll down, you could get the lower quartile. You could get the min, the max, the lower quartile, the median. If you use your calculator, all good ways to find that stuff, right? So min, max, Q1, Q3, and standard deviation, and mean. So in this case, 2.09. And then look at next. Calculate the standard deviation of GoFish. Oh well, I have that already, right there, 1.27. Now with a little curveball at you, what if I want the variance? Now this is not a formula in a formula sheet, but you have to know it yourself, right? There's a relationship between variance and standard deviation. And the way I always said to remember it is I remember that variance is the bigger one. This is bigger. So variance is bigger. So I have the standard deviation, so I got to get bigger. So, sorry, variance and standard deviation, variance is bigger, so you have to square standard deviation to get it. Right, it's a square root relationship. So right, you either square it, you either square or you square root it. How do I keep that in mind? I keep variance is bigger. Right now I have the standard deviation, so I want to make it bigger, so I'm gonna square it. So variance of this will be 1.27 squared, whenever that happens to be. Actually, let me clean some stuff up first. This should be years, right? Sending here. I should label my axes. This was years, and this was cumulative frequency. Right, so this is how that all shows. So it's years, blah blah, cumulative frequency. Now we actually use a graph here. Use your cumulative frequency graph distribution to estimate the median lifespan of goldfish to one decimal place. So now notice it's the median. I could do that on my thing here. So the median lifespan, right? So there's 200 goldfish here. Median would be halfway 100. Go across, and you go down. One decimal place. This is a pretty crappy drawing. So Wilson put 1.7 years. But again, on the IB test, we had a much nicer drawing. I just kind of did that, right? But that's how you do it using your frequency graph, right? Median's half. So there's 200. Halfway would be 100. Go across. Remember, every time you use this thing, you always have to use the graph. Go across, go down. Don't just go, oh, 100 done. No. Go across, go down. If you're using something here, you go up and across. If you're using the graph, you use the graph. A goldfish is considered mature if it's more than 2 years old. A goldfish is like the random was probably that it's not mature. So mature is more than 2 years old. So over here, all this is mature. Right? So now if I wanted to find the probability to get mature, I would go here, go up, go across, and I have to use a top half because mature is a top half. But in this case, they threw a little curveball. What's probably that it's not mature. So when I go up and across, let's say that's like 180. What am I talking about? Let's say that's 110. Let's go 118. Right? So that value is all the values that's from 0 to 118. So about 180 of them are not mature, right? But they want the probability, so I'm gonna put that over the total, right? They want the probability put over the total, which is I believe 200, and that's the probability that it's not mature. You could leave it as a fraction or put it as a decimal, either way you want to go. But that's the idea, right? Anytime you go above, and so anytime it's like the top half, it's more than, greater than, use the top half, go up across, go from here. Anytime it's less than, like in this side, not mature. Bigger than that's mature, less than it's not mature, you just use the number. Next, let's talk about some probability terms. So A U B is A union B, right? So it's a union. Remember what union means? It could be in A or in B or in both, right? So it's in either of these, right? So it could be in A, it could be in B, or it can be in both. Intersection is much different. Intersection is and has to be both. So intersection is both A and B, right? So it has to be in both of them. Very important, right? Union means either. So I could have this or that. I'll be happy with either one. So all those work, including both of them, right? It could be that, or both. Intersection has to be both of them. I need this and that. I can't just give me one of them. It has to be the inside. And then next up is our favorite, given that. So remember, anytime you see given that, that's the line. So this would be probability A given that B occurred. So it's saying, what's the odds that A happened given that B happened? Now, on the formula sheet, it's not going to be like this anymore. It'll be written this way. Probability B times probability A given B equals probability of A intersection B. And then the general idea is anytime you hear this, for the most part, unless it's Venn diagram, just use this formula. Plug it in. We'll do a couple examples. A little more vocab. Complementary events. Right? All that means was A or not A. Now, this is a formula. It's the easiest thing in the world, right? If I say the probability of A happening is 3/7, the probability of not A happening, it's the rest. It fills the hole, right? It's the rest. So 4/7. So that's all it is. Complementary events, they add up to be 1. General idea. Mutually exclusive events. Now this form is actually in your formula sheet. Mutually exclusive sounds kind of funny, but this means that they have nothing in common. They're mutually exclusive. So this one's by itself and B is by itself. They're both loners, right? So they have nothing in common. So they do give you this formula. You can always, if they ask you, are these two things mutually exclusive, you can use this formula. Or you can understand, hey, mutually exclusive means they have nothing in common. So this is true when it's mutually exclusive. So either way it works. So if they ask you, are these two mutually exclusive, you can use the formula to check it. Or you can just be like, yes or no. No, they have nothing in common. Or yes, they have nothing in common. Or no, they have something in common. Now, this is my favorite formula for stats because it always works. So anytime you're doing a stats problem that has to do with probability, this is the problem we're going to use because it always works. So even if it's mutually exclusive, that's a 0. It still works. So anytime you have to look for the union and you don't have it, right, you can use this formula. If they give you the union and they give you the intersection, they want you to find probability of something happening, use this formula. Basically, always use this formula. Oh, that's awful. Always use this formula though. So it's super important. Always use it. It gets you all the probabilities you need. Next up, independent events. So these are events that have no effect on each other. So they're independent, they have no effect on each other. Now, a lot of times they're going to ask you if these are independent or not. And the easiest way to do it is the formula giving you a formula sheet, which is this. So again, you could only use this. You could only use if they mention it's independent. Right? So they're going to say, hey, these things are independent, or they're going to ask you, are these two things independent? Then you can use this formula. Other than that, don't touch this thing. Touch my favorite one right here. It wants to be used. It likes it. So over here, right? So let's classify this as independent or non-independent. Tossing a coin and rolling a die. Well, they have no effect on each other, right? If I toss the heads, that can affect me rolling die? Not at all. So these are independent. How about drawing 2 clubs from a deck without replacement? Now the key word here is without replacement. Anytime it says that, you know it's automatically dependent. Why? Because of this. So deck of cards has 52 cards, right? The odds of getting the first club, I can't draw a club. Let's put C. Well, it would be 13 out of 52 because there's 13 clubs in the deck and there's 52 cards. Since we're doing without replacement, I'm not putting that card back. I'm holding that card. Can't take that card away from me. It's mine. Well, I'll draw the next card being a club. Well, now there's only 51 cards in the deck because I drew a club the first time. And actually, there's only 12 clubs left. Right? So that's dependent, right? That what I did in the first turn affected what I did in the second turn. Compared to this one where I toss a coin, I have a 1 in 2 chance of getting heads or tails. Rolling a die doesn't matter. It's a 1 in 6. It's a totally different odds. Right? So that's the difference between independent and dependent. And the general key that they said without replacement, it's dependent. every single time. Now, there might be other times where it's dependent. You just gotta look at what's going on. And by the way, if you want to actually find the probabilities, you multiply these and get your answer. Same thing over there. Okay, let's talk about conditional probability. Now, we mentioned it before, but now we're going to go into it, right? So conditional probability, you're going to see it's a lot. They'll add it to lots of things. The general idea is, right, if they say given that, that's a conditional probability. And we're going to use this formula from your formula sheet, where that's the given that line right there is the given that form. And all we're going to do is plug it in. Now, a lot of times they want you to find this probability. A lot of times that'll be your x, but not always. Sometimes they'll give you the probability of the given that, and you got to find something else. That's a given them problem. Let's do some examples of putting all this stuff together. So first here, let's do a Venn diagram, because I know everybody loves Venn diagrams. So there are 82 students in grade 12 at school. 64 students take math, 56 take Spanish, 12 students do not take either. Who are those kids not taking math? Anyway, how many students take both math and Spanish? Now, before I can answer that, let me fill a couple things out. So my universe here is 82. I have 82 students. A couple other things. 64 students, 56 take Spanish, 12 students take neither. So those losers are out here, not taking math. So like that. Now, I know 64 students take math and 56 take Spanish. Now, keep in mind where you put these. I personally don't like adding them onto this graph because I think it messes people up. But if you are, the 64 math is not this part. It's the whole circle. So the whole circle is 64. So if you must put it like up here, it's not this thing, it's the whole circle. Same for Spanish. That 56 Spanish students is the whole circle. So 56 up here. You would only put it on this side if it said only Spanish, and then you put it on over there. But Spanish in general is just the whole circle. So kind of like that. Again, I'm not a big fan of putting those there because I think it messes people up. Anyway, so how many students take both math and Spanish? I got to figure out this right here. How do I do it? Well, first you got to figure out what this is. The whole thing is. You're like, well, how do I do that? Well, you go back to my favorite stats equation right here. Right, so we're going to use that formula. So probability of M union S equals the probability of M plus probability of S minus the intersection. I can't fill it in. So we have probability of M, and actually instead of doing probability, we're just going to put the number. So same idea, because we just want the number. How many? So same idea, just number instead. Math is 64. Students is 56. We're actually looking for the intersection. That's X there. Now, I don't have this, so this is the first thing I do. How do you figure out what the union is? Well, very simple. There's a formula for that. Formula is not like canon or anything. It's not on your formula sheet, but it's one you should know anyway. And that is the universe is equal to the union, so M union S, plus the neither. I'll put like a line for neither. And that's what it is. It's always the same thing. So right, if you add up this union here plus the neither, the outside, you get the whole universe. And I know my whole universe is 82. I don't know what that is, but I know the neither is 12. So you subtract that from both sides, and you get the union equals 82 minus 12, which is 70. So that's how many people are taking either math or Spanish, right? Either one of those. So this is 70. Now we can just do some basic math. If I go 64 plus 56, that's 110, 120. I can do math. Minus x. Do some little math here. You're going to get x equals 50. So that's how many people are in the middle, right? 50 people are taking both math and Spanish. And what that means here is, since I know math is 64, that there's 14 leftover people only taking math. Those are my people right there. And over here is 56, so 56 minus 50 is 6. People are only taking Spanish, losers. How many students take both math and Spanish? We just figured out it's 50. Now here's our favorite. Given a student takes math, what's the probability that he or she does not take Spanish? So let's just write this down in the formula. So given he takes math, so probability math. What's the probability that he or she does not take Spanish? So Spanish with a little not sign. Now there's two ways to do this. I'm gonna do it first using the formula. So if you follow my formula, the one up here, right? So you just kind of plug in the way you see it. So this is not Spanish and math, which makes A right here is probability of math, and then that makes this part math and not Spanish. So let me put that all the way down here. So it gets multiplied by probability of math, and it equals probability of math and not Spanish. So how does this work out? Well, probability of math is 64. Now technically I should put 64 over 82, but it's all gonna kind of work out anyway. Now this is what I'm looking for, right? That's the question. And over here, math and not Spanish. So what are the odds you're taking math and not Spanish? See, this part you always gotta think about logically. So math but not Spanish. So that's this part. Right? These are the kids taking math and not Spanish. So you can put a 14 there. Now again, technically it probably should be like this. Equals, because it says probability. So intense probability plus put over the universe, but it's going to kind of work out anyway. If I solve for this, I'm going to get x equals 14 over 64. And again, we're in IB, so you don't have to reduce. Right? And so again, that's the probability that student takes math, given that student takes math, that they do not take Spanish. Let's do a couple of things here. Now, if they ask you, show that these two are these two things mutually exclusive, you'll say no right away because there's a thing in the middle. Done, right? Now, how about they say, show that the M and S are not independent? Remember what I said earlier? The only time you use a certain formula is when you hear the words independent. So if you hear independent, you go up on your formula sheet. Oh, right here. It said independent. I could use that. So in this case, that's going to say probability of M intersection S should equal the probability of M probability of S. And all we do is plug it in. If it works, it is independent. In this case, it's saying show it's not, so it shouldn't work. Right? But M and S is, we just 50 over 82, right? Probability of the intersection, 50 over 82. That's what this is. Does that equal probability of math? Math is 56, 64 over 82. And probability of Spanish is 56 over 82. You can actually do the math on this. And if you do it, you look right here, you get, they don't match, right? This is 0.610 and it's like 0.533, so they don't equal, so it's not independent. Right, so again, you can only use an independent formula if they actually specifically tell you they're independent or if they ask they're independent. Otherwise, you don't do it. And if they ask about mutually exclusive, it's easy if you just understand what it means. It means they have nothing in common. So look here, these have something in common. Otherwise, if you're not sure, you can use the formula for mutually exclusive. But that's a Venn diagram. Now let's do a tree diagram. So example, a standard deck of cards contains 52 cards and 4 aces. A student selects a card from a standard deck and records it whether or not it's an ace. Without replacing the first card, he selects a second card and records it with whether it's an ace again. Complete the following diagram. So again, all he's doing is picking a card and seeing if it's an ace or not. And without replacing, again, very important, right? And we'll talk about that in a second, why it's so super important. So first, he picks a card. It's either ace or not ace. Odds of it being an ace, well, there's 4 aces out of 52. Odds of it not being an ace will be the rest, right? The complement of that. So that's why we put A and then not A. Will be the rest of it. 48 out of 52. So 4. So we do it again, right? Now it says without replacing, super important. So we're not going to replace the card. So that means that all the values go down 1. Right? I had 52 cards to go start off. It took a card, so now there's only 51 cards total. And in this path, we took an ace. So there should be 1 less ace and 1 less card total. Which means over here we still have 48 out of 51. Down here, the opposite idea. We didn't pick an ace the first time. So odds of getting not an ace is 1 less out of 51. And the odds of getting an ace is still the same. We haven't picked it. So 4 out of 51. So something to that effect. Now these you can fill out each one, but what's the probability of drawing exactly 1 ace? So right, odds of getting exactly 1 ace. So the way that works is this. If I go up here, I got an ace. Now I only want 1 ace, so I got to go not ace. So ace and not ace, which would be 4 out of 52 times 48 out of 51. But that's not the only way to get 1 ace, right? I could do the opposite. I could go no ace the first time, and then ace the second time. So anytime that happens, anytime you have more than 1 string, you put plus, and then we'll go not ace and ace. So 48 out of 52 times 4 out of 51. And that's odds of getting exactly 1 ace. Now if they said at least 1 ace, that'd be 1 ace or 2 aces. So you have to add this third line right there. Another given that the first card is an ace, so probability first card is an ace. What is the probability that another card is an ace? So what's the probability of getting an ace given the first card is an ace? So I'm just going to use the formula. Right? Our formula, again, it's on the formula sheet, is probably ace. Ace times the probability of ace equals probability of ace intersection ace. And all we got to do is fill this out. So again, I'm looking for this. And now I got to find what probability of A is. Now probability of A is just straight up probability of A. Right here. Right? Probability of ace. 4 out of 52. Now a lot of times I'd like to build up and I'd like to use the answer from here, but this one's slightly different. What's probably getting an ace? Well, there's 4 aces out of 52. Now, probability of ace ace. So what's the probability of getting ace and ace again? Well, that'd be this one and that one, right? Only we could get ace ace. So that's gonna be 4 out of 52 times 3 out of 52. 51. And then from here, you just have a math problem. You can solve it. And if you do it correctly, these would cancel out. And you just get 3 out of 51. Right? So that's a tree diagram. Those are my personal favorites. I like those. I think they're easy, but we'll see. Last thing. Expected value. I mentioned this before. You can find your formula sheet. Right? Expected value is right there. But it also is right here, right? E of x, e of x. Expected value just means mean. What do you expect to get? You can either use this formula, which is multiply your x's times probabilities and then add them up to sum, right? That's what that means. Or just multiply your probability by the number of terms you have. Right? What do you expect to get? What's the average? So this is this problem. Expected value questions rely on both probability and some sort of quantifiable value. Sometimes it's money. Consider a game where a student rolls a cubical die. It's a die. It's a normal die. If the die shows a 6, the student wins $9. If the die rolls a 1 or 2, the student wins $6. If the die shows 3, 4, 5, the student wins $1. So let's actually like write the odds of this game. Right, so 1, 2, 3, 4, 5, 6. Right, odds of getting to 1 are 1 out of 6. Odds of getting 2, 1 out of 6, 1 out of 6, 1 out of 6, 1 out of 6, 1 out of 6. Right, but actually I don't really care about those odds. I care about the odds of me making money. So I could win $9, $6, or $1. Odds of me making $9 if I get a 6, so it's a 1 out of 6 chance of me making $9. Odds of me getting $6 if I get if the die shows a 1 or a 2, right? So these are the odds of me getting $6. Since there's only one row, I'm just gonna add them up. So it's 2 out of 6 of a 2 out of 6 shot. And if me winning only $1, right here, all 3 of these, so that's gonna be 3 out of 6. So those are my odds. Those are my winning odds for everything, right? Now find expected value. So right, again, if you look at your formula sheet, we're going to use this one right here. So expected value is this x times p. So the expected value is this x times p. So what does that mean? Well, here's my x, and here's my probability. So I'm just going to multiply 1 times 3, 6, plus, because if you remember, expected value was that summation notation, which just means sum. 6 times, that's my x, times 2, 6, plus 9 times 1, 6. And you get 3 out of 6, plus 12 out of 6, plus 9 out of 6, to keep it easy, count on the common denominator. And I get 15, I get 24 out of 6, which is about $4. So my expected value is this $4. Now, the cost is $4.75 to play. Is this a fair game? So fair game just means expected value should equal the cost to play. That's a fair game. No one makes money, no one loses money, right? It's still unfair if you're making money. If it costs only $3 to play and you're gonna make $1 each time, it's still unfair, but I would recommend playing it. So is this a fair game? No, right? It costs more than you expect to get. So only time it's fair is in this case. So not fair. Ralph plays 30 games. How much money do you expect him to win or lose? Well, let's look at what's going on, right? I expect to win $4. It costs me $4.75 to play, so I'm gonna be losing 75 cents each game, and I'm gonna play that 30 times. So 30 times 70 actually is $20.50. So I expect to lose on average $20.50 if I play that many times. So that's the idea for that. One last thing before I go, and that is stem and leaf plot, just because I'll make sure you know everything. You guys ever seen a standard leaf plot before? That's this. So you'll see something like this. 1, 2, 3, 4, 5, 8, 9. What a standard leaf plot is just a way to write out values. So this is the same thing as saying, hey, 21, 32, 33, right? 34, 35, 48, and 49. Right, so that's all a stem leaf plot is. So if you ever see this, that's all it is. It's just a way to write out numbers in a fancy way. So if you want to find the mean, well, you have your numbers, plug in your calculator. You want to find the median, well, you have your numbers. You can find the middle, which I believe is this one in my case, 34. Right, that's all it is. So, and that's it.